Good afternoon. My name is Santosh Rao, and it's a privilege to be here today. I have the distinct honor of having been in front of this group the very first time this was webcast back in 2010. So some of you heard me say that last time I did it. So SFD4, I believe that was back in 2010. We were talking about ONTAP 8.0.1. That was my first appearance in front of this group. Survived then, but didn't get called back till 2018. So barely survived, I guess. I am fortunate to be back again. I know we had a great session last year, and very much appreciate the opportunity to be back again. I lead a team here at NetApp that is focused on our AI offering from NetApp, and we are a team of data science engineers, data infrastructure engineers, vertically focused solution engineers. And we've come a long way since I last stood here in front of you. A year and a half ago, when I was here, we were talking about the evolution of Hadoop and the evolution from Hadoop to AI. And at that time, it was a strange conversation, I guess. But today, we've got AI much more in the headlines and Hadoop much less so. There's a lot more shift in the vendors when you look at Cloudera, Hortonworks, MapR, and so on. And so we'll talk about where we've been, what we've done in the year and a half since we last saw you. So first, let's just introduce what we mean by NetApp AI and what is a full stack AI and what it means to run from edge to core to cloud. We've talked in the past about data pipelines and the fact that data has its own life cycle, starting from ingestion to data aggregation and data curation, cleansing and preparation, and then the process of applying machine learning or deep learning using acceleration techniques, whether it be Spark-based machine learning or, more interestingly from our perspective, GPU-accelerated deep learning. And so what we see here is that life cycle of data is actually an instance of what NetApp has been working on called the data fabric. So data fabric for a NetApp perspective has been hybrid cloud, and clearly the edge is very much now a part of that fabric. Going from edge to core to cloud is that whole life cycle of data fabric. So specifically, what does this entail? You're looking at systems at the edge that have a small form factor, that are software defined, that can quickly destage data, and perhaps work through last mile infrastructure that is able to get near edge solutions. In the data lake, when we talk about data lake, these are really a collection of data sources for structured, unstructured, variety of different databases, maybe file systems or S3 data lakes and so on, that are then used to aggregate data, curate data, and then feed data into these training systems. Training is probably the biggest part of the change that we've seen in systems architecture, and that's where I'll spend most of my time, going into training and a little bit into inference. But as we look across our NetApp portfolio, what we have brought to bear here is a pod-like architecture, which is where I'll spend most of my time, focusing on training compute with storage and networking that delivers the high performance that you need for these immense training jobs that may run weeks or even months on end. So what are the use cases that are driving this whole space around AI? Why are we seeing so much uptick in this space? We have, since the last time I stood in front of you, we've actually had over 50 customers deploy AI solutions. And we have hundreds more where we're seeing active engagement. And I'll take even a simple example like smart cameras and smart cities. I mean, the potential is immense when you start looking at every city that is thinking about what smart cameras can do for surveillance, for public safety, for smart traffic management, and so on. And we are now seeing an ecosystem that is simplifying AI, so much so that there are software vendors talking about code-free AI. Code-free AI, as in you've got a library of models, you've got data that is being gathered, and you can start applying models to data to start looking at use case level applications. So when you look across these verticals, across these use cases, we're seeing a rapid uptick in particular verticals. So automotive is no surprises, but so is the case with healthcare, with financials, with telco service providers, and public sector as well. Each of these, we're starting to see almost every major provider in that vertical starting to go after these use cases and look at how they invest, what is their first investment, what is their next use case, and so on. What does NetApp bring to this space? We have built out converged platforms that start small and scale big. These are platforms that we build in conjunction with NVIDIA, with the DGX server line today. And we have started to broaden that beyond NVIDIA to include server partners like Cisco and other partners as we look forward. Recall, we talked about the pipeline as encompassing data lakes, training, inference, and the cloud lifecycle. This is one part of that pipeline, but it is where a tremendous amount of budget spend is happening right now. The reason for that being the high performance nature of these workloads, the thermal and cooling considerations that go into these workloads. As an example, these servers are 3.5 kilowatt each. When you look at the 10 new servers, the DGX2, those are 12 kilowatts each. If any of you will be at Supercompute next week in Denver, we will have some fascinating displays of real hardware running in liquid-cooled cabinets with negative air pressure. Those are cabinets that are hosting upwards of 50 kilowatts per cabinet, 50 kilowatts per cabinet. So as you start to look at this hardware, there's a tremendous amount of supercompute being brought to the masses. So the real transformation that's happening here is what used to be supercomputing, only affordable to extremely expensive HPC centers, is being brought to the masses, is being brought to the enterprise, and is transforming computing as we know it, and changing use cases that were unsolvable in the past. So that is
so just to try and translate that and read it back to you, if I may, what you're saying is you're using your years of hardware design experience from building storage arrays and then redoing it for GPU clusters or TPU clusters.
We're using our years of experience with FlexPod, which is our converged infrastructure, to start to build pods for the AI market with a variety of compute offerings, the best of breed being NVIDIA DGX compute. This is the NVIDIA DGX.
Right.
And we're starting to expand that across a choice of compute vendors, whether that be NVIDIA, whether that be Cisco, or any of our server partners. But more importantly, we're expanding it into a choice of cloud as well. So
you're going to get a cloud to host these units?
So when we talk about edge to core to cloud, the software stack that runs on these units can run in the cloud. The hardware can run near cloud in co-location service providers. I'll talk about that in a little bit. And these systems can run on-premises as well as at the edge. And the NetApp Data Fabric starts to build a federation across that, creating an edge to core to cloud pipeline that we call the NetApp AI control plane that I'm going to
So the hardware is one thing, and then there's a software pipeline on top to run their tasks.
Exactly.
The neural nets and stuff like that. Okay, great.
So there are 4 elements to something as complex as this. Firstly, AI is entirely focused on data scientists, and they don't understand hardware. So we want to abstract out as much of the hardware, and the way we go about doing that is simple automation. We use Ansible to completely automate the deployment from rack and stack onwards to bare metal provisioning with Ansible. And once we've done that, we use Kubernetes in Kubeflow to be able to automate the lifecycle management with our AI control plane. Delivering performance on these systems is a function of both capacity, scale, and the ability to do random and sequential workloads. And I'll actually go into some fascinating detail on what we've learned in those over 50 customer deployments. We'll go into what does that pipeline look like, what does system architecture look like for this system. So first, the hardware itself. It is a 100 gig system as far as Ethernet is concerned, also offered with InfiniBand and our EF series product, but clearly a 100 gig high performance network ingress system. The reason that these are high performance network ingress is because you've got to look at these pipelines as constantly flowing data. So let me take an example. We have a financial customer doing 50 neural network training jobs that are running in parallel. And these 50 jobs have about 20 terabytes of data that they're pulling for the footprint to train those jobs. Which means if the training job runs for a day, every day you've got 15 to 20 worth of data flowing through that pipeline into these training platforms. So imagine these platforms now starting to become freeways where you've got enormous amount of data traffic flowing through constantly running a training job. Once you're done with the training job, the next one comes in. That's just going to get more and more clogged. You can't build wide enough freeways fast enough, so what do? You push hardware to the edge. You push AI training jobs as close to where the data is ingested and as decentralized as you can. And that's a perfect use case for the data fabric. What the data fabric is all about is a fabric of endpoints. And the edge is the new killer app for that data fabric. And just like we were talking about data fabric 6 years ago when nobody else was talking about it, we think that AI now gives a whole new life and a whole new set of use cases to the data fabric.
Well, your data has to be close to your TPUs.
Absolutely.
Because you're thumping the data around at very high volumes.
The number one question, which we will go into in system bottlenecks and architecture, is the VP of IT saying, I spent $1 million on this hardware, I'm not getting 2% utilization, what are you guys doing? So we'll go into exactly what that conversation entails. But first, what we bring to the table is the seamless scale of cluster on tap. The conversation we were having in 2010 that's paying off for us now. 2010, we talked about all the benefits of seamless scale out. And here is an example where data in petabytes is an everyday enterprise conversation. In fact, I talk to our teams as there are 3 steps in an AI journey. The first step is about 100 terabytes of data. The customer is just starting to experiment with AI. They want a single node AI system with about 100 terabytes of data to give them AI training. That's the starter solution. Once you've gone from there, the next step is you're going to build a POC that you're taking into production for one use case. Maybe it is traffic surveillance, just one use case, one line of business. So that then starts to expand into about a petabyte of data. You've got a petabyte worth of trained, labeled data that is going to go into production management for that pipeline for one use case. Now let's expand that into maybe it's a city or state local government and all of the use cases for that particular line of business. You start to get into at least about 10 petabytes of data. And as you expand into the full subset of all of the lines of business for the state government and all of the use cases, you're looking at 100 petabytes of data. Now, what is common across that 100 petabytes? It has to be a namespace that is accessible for retraining. So what has changed between 100 petabytes of data in the cloud and 100 petabytes of data for AI is that you need to be able to pull up data randomly out of that 100 petabyte data lake. Why do you need to do that randomly? Because of bias. AI algorithms cannot afford to get overtrained on a selective subset of the data. So what you need to do is constantly open up the data lake, constantly do random selections of data for retraining, and that process could happen every 2 weeks, could happen every month. And so here's a fascinating story now where we've gone from being able to build massive data lakes to now saying, I want to randomly read anything in that 100 or 200 petabyte or even an exabyte data lake. How do you do that? So those are the interesting system architecture challenges, the performance challenges, the data tiering challenges that start to open up design and possibilities. Now, when we talk about these systems, we are actually deploying large-scale systems. If you Google for SPER Bank, SPER Bank is the world's largest AI supercomputer deployed on NetApp. It actually looks far more menacing than this. All I have here is the compute. Obviously, I'm not showing the drive shells. But the SPER Bank is 75 DGX2. Each of these is a DGX2. Each of these is 12 kilowatts of power. And we're talking 75 DGX2 being deployed at SPER Bank. We've got telco providers in APAC that are deploying 25 of these. We've got supercomputing and scientific computing facilities deploying 70 of these. And so last year when I stood in front of you, March, I think, of last year, this was a concept. Today, this is being deployed. And I've been here a long time. I saw many technologies right through. I did not see this kind of uptick. We'd see people buying one server and saying, OK, I'm going to kick the tires. But to go from where we were at conversations to seeing financial customers, telco customers, government, federal and state, not just in the Americas, but worldwide, Eastern Europe, APAC, Mid East, deploying these kinds of massive systems is eye-opening for us.
how easy is it to switch out the DGXs? Because those GPUs, TPUs, they rotate fairly quickly.
The DGXs bring with it the NVLink backplane, which really gives you the ability to do linear scaling across more than one GPU complex. So when you're looking at what is it the DGX does, the magic sauce in the DGX is the NVLink. It allows you to get that linear scaling of performance as you go beyond 8 GPU into 16 and beyond that into tens of these nodes.
The problem that we have, or I've seen, is that quite often you end up with orphan clusters of GPUs that aren't worth running because they're so slow after 3 years that they're not worth powering anymore.
That's a great lead into a conversation I'm going to have about what we're doing with service providers.
I knew that.
Service providers are filling in those shoes to say, you know what, we'll take the CapEx cost and we'll make data scientists productive.
Yep.
You just don't need to go into a public cloud and move your data, petabytes of data into the public cloud.
Yep.
The challenge that customers have is data has gravity. You can't move 100 petabytes of data. If it's not in the cloud, you got to work where the data is.
Yeah, you can't afford to put 100 petabytes in the cloud because of the network transfer rates.
And you got to think about egress costs. This is not a one-way traffic. This is two-way traffic, because when you train a model, you're going to push the model to the edge. If that model is a neural network on your phone, and you got 300 million phones deployed, that's 300 million phone updates being pushed to the edge.
Yeah.
And imagine if that data model was being trained in the public cloud, you got egress traffic that is driven by a function of the edge endpoint. So there's some fascinating system design there.
So are you on the top 500 list at all? Are you powering any of the top 500 supercomputers?
We are certainly powering the top AI supercomputers. So when you look at the largest AI deployments in APAC, we are deployed with them. When you look at the largest, like I mentioned, the largest AI supercomputer in EMEA, we are deployed with them. So we've got deployments on some of the biggest ones.
And so who is the market you're going after for this? Is it the research, or is it more the commercial side?
That's a great question. I get asked this all the time. And what is most fascinating to me is what used to be research, computing, high-performance computing, is coming down to the enterprise. And this is the biggest transformation that is happening out there. Things that you could not afford to do unless you were a Lawrence Livermore Labs or NASA or something like that is coming down to the enterprise in liquid-cooled cabinets that are self-contained. We are not talking about massive plumbing to run water cooling through your data center floors. We're talking about cabinets that are self-contained. So this technology is coming to the enterprise and is coming to service providers who are making it affordable for the enterprise. So it's not just enterprise as in your Fortune 100, Fortune 500. It is mid-market customers that have to compete with Walmart and compete with Amazon, but that can do that using service providers. And of course, they can do that with the public cloud. So what does it take? It takes an entire village. And we call that village NAPN, NetApp AI Partner Network. Starts with, obviously, the infrastructure, which begins with partners like NVIDIA, but a choice of compute from our perspective. So we're in a good spot here because we look at data as the new gold, and that gold has a longer life than all the containers that carry it, which is the compute ecosystems that go with it. So as you look at these data pipelines and these data assets, they're going to live a life of decades. And we're going to hopefully be the host of that data, working across a choice of the rest of the ecosystem, which means a choice of compute, a choice of software ecosystems as the data sources for that data changes over time, a choice of partners that will deploy worldwide, and more interestingly, different types of consumption models, whether it be public cloud or service providers. All of us saw the 2008 VMware wave. 2010, we were talking about virtualization, and we saw the service provider uptake for VMware at that time. You're seeing the same rise of service providers now, driven by 2 or 3 factors. The first is we talked about power and cooling. Customers can't build data centers that can host 50 kilowatt racks. They're blowing out power for their entire data center floor. So they're looking at who can host this for me, especially when you look at racks that are tens of these racks. So an entire new market of service providers, names that we may or may not know today, but that are emerging and changing the space, are starting to come up. And I'm going to give you a sample of this. We're working with over 10 service providers, jointly with NVIDIA, on a program to bring 3 types of alternate consumption models for AI. Now, here's the most fascinating thing. A year and a half ago, I didn't know these names. I couldn't talk about these names with you. We are moving so fast that in a year and a half, we've created a whole ecosystem, and put in place a service provider ecosystem. And we've got 3 types of deployments that we're starting to incubate with these service providers. So what are these 3 deployments? The first is the most basic, which is every colocation partner should be able to host hardware. That's the most basic definition of a colo partner. That's in place. The second is a test drive. By a test drive, what we mean is we incubate the rack at the partner. A customer can try it out as much as 3 months. They're happy with it. They choose to deploy in their data centers or choose to deploy at the service provider. The third and most intriguing is AI as a service. And the service providers are trying to distinguish themselves from the public cloud in saying that you can consume AI by the month. So you can come in and say, I want a POC project. Maybe I need 3 months of GPU compute infrastructure with data co-located, and I can consume that as a service. And to your point, if the hardware needs to be tech refreshed, that's your problem, Mr. Service Provider. It's not my problem.
All right. So the couple of questions is, so what you're saying there is that the GPUs and the TPUs are like chassis level, so I'd have to replace the entire chassis, which is as I expected. Like there's not some magic going on here where I can slide them in and out as I need to. That's what you're saying.
Yeah, and the reason you don't want to do a GPU level replace is because the overall system performance has to evolve with these GPUs.
But you're saying the internal architectures, the backplane buses, and all that sort of stuff is also evolving.
Exactly.
I guess the other question here is that if the biggest challenge about moving into a colo is the same as moving into the cloud, you've got petabytes of data to move around, and colos are often ill-prepared for that. They're often under-specced bandwidth-wise. And the other challenge that I've seen people doing this type of class of data compute, I call it data compute, not AI, because data compute's been around for decades, it's not new, is when you try and move that data out, it takes days or weeks. So one of the problems that we've been facing is building custom apps to shift petabytes of data around, even on a 10 gig or 100 gig internet pipe, is weeks or months of time.
And that is where smart technologies from NetApp like FlexCache come in, where if you've got your master data co-located, let's say, in a data center in Utah, and you've got the colo provider maybe in Hillsboro in Oregon. Now you've got the ability to take a FlexCache cache volume that is placed in Hillsboro with the origin in Utah. And you do all of the data prep in Utah. So you look at CPU infrastructures that may be co-located by the master data in Utah to prepare the data sets.
Yeah.
Now, there's a difference between data lakes that may be petabytes in scale and cleansed, curated, labeled data, which is a smaller fraction of that. So as you start to look at these training cycles, you've got these data curation jobs that are running close to the master data, reducing the footprint down to labeled data sets.
Yep.
And now the labeled data sets need to appear close to the GPU.
So what you're saying is you redact the data at source, try and cleanse it in some way. That's going back to the old days of ETL, data ETL load, where you had to take the data out and then clean it before you did anything with it. That's not what we're trying to achieve with AI, surely.
No.
Well, that's where the brute force approaches start. Now, where it evolves to is semi-autonomous labeled data close to where the data is being ingested, where the data is being conceived. So over time, constantly you're going to see a left shifting of intelligence moving to the edge, which means you're going to see filters, AI inferencing filters at the edge that start looking at bifurcating your data as it's coming in, looking at labeling data as it's being ingested, semi-autonomous and autonomous labeling as it's being ingested. So it's just a fascinating time. If you're a data geek, as all of us are, and we sort of look at what is compute doing to this data and what is system architecture evolving.
I get what you've said that several times, so I'm sort of trying to bunny hop over the marketing hype you keep spinning out. And the other challenge I've got with AI is it's moving so fast that if customers get into it, like the struggle that I've seen is a lot of people who are in enterprises, they don't understand AI infrastructure at all. They don't understand moving petabytes of data around. They don't understand low latency networking. They don't understand GPU clusters. They don't understand backplane architectures in the servers and how to optimize. They're not even used to the idea of a 15 kilowatt rack, much less a 35 or a 50 kilowatt rack. Do you struggle? How much effort do you have to put into selling this product? Because usually you have to ram it down their throats, and it takes 10, 15 sales reps and TMEs to make it work.
And this is where we have completely changed our approach. We are building fully automated AI control planes that automate the rack and stack and then the deployment with Ansible, and then build an AI control plane with Kubernetes and Kubeflow that I'm going to go into and show you what that looks like. So this conversation 9 months ago, I said, yes, that is a challenge.
Yep.
Today, we can give you a Jupyter notebook as a service, and you can pick if you want 2 or 4 GPUs, and off you go.
Okay. All right.
So we have put programs in place, like I said, try and buy AI as a service, and we are adding service providers that go with it. But let's take a step back and look at what is a data pipeline? What is an AI pipeline? And what's going on under the covers on the software side? So you're starting out with data ingestion, feeding it through a process of firstly cleaning the data, labeling the data, where you're applying supervised learning, perhaps applying some feature engineering. And then when you get into training, the data scientists are looking at what frameworks am I going to operate on, what parameters am I going to tune, performing the model training itself, evaluating the results of that model training, and then start to build out deployment and inference. So the pipeline, when you start to double click on it, is a variety of these stages. Now, what is interesting is each of these stages is a performance bottleneck. You've got data bottlenecks with ingestion. You've got aggregation bottlenecks across multiple sites. CPUs become a bottleneck when you're looking at data prep on CPU clusters. And then the obvious conversation around training bottlenecks. And what system architects are doing right now is looking at how you solve each bottleneck across these stages. Can you start to offload from CPUs to GPUs? Can you use RDMA to offload the network ingestion? Can you shift left with some of this intelligent processing to avoid the bottleneck in the core? And what do you do to move the entire process to the edge so that you're never coming into the core to run this life cycle? From the life cycle of a training job, there's 2 things that we're looking at. We're looking at data, and we're looking at frameworks. And when we get into data, we start looking at what is the type of data. Is it structured? Is it unstructured? If it is structured, what is the data source? Is it a database? Is it a GPU database? Can it be co-located on the GPU compute? If it is unstructured, is it file? Is it object? Is it parallel file systems? And so those are the choices. You start getting down to, okay, what is my data type? What is the data source? How many data sources? Where are they located? Close to GPU or a cached instance by the GPU. And then the frameworks, of course, which is every developer or data scientist has their own choice of framework. When you get into the actual data that is being trained, these files that are being trained, depending on whether it's image, video, or audio, you have random reads of images, which is the most basic type of training file read. Or you've got aggregated images in the form of TF record, that's a sequential read, or a sequential read of audio or video streams. One training job may run as much as a month. A really complex training job may run an entire month. More typically, it's probably a day or a couple of days. That epoch or that training life cycle is one run through the training infrastructure, and then off you go again. So let's look at what does that all imply. So we're taking data in the form of images, random images, feeding it through these neural networks on GPU compute hardware. Layers of these neural networks are operating on different sets of hyperparameters, producing an output from that neural network that eventually turns into a trained neural network for that use case, using different types of neural networks for different use cases. The thing they have in common is random reads of images or video or audio files, significant amount of compute processing, while parallel reads continue to occur into the CPU pipeline. So this is a phased job where CPU is reading data from I/O into CPU pipelines, staging the data, while the GPU is operating on the training jobs, and then more data is fed in from CPU into GPU. The more the number of layers, the more compute intensive the job. The more shallow the network, the more data intensive the job. And on that note, you get into the conversation around training and inferencing. So training and inferencing are important because these are entirely different infrastructures. Everything I showed you so far, those 12 kilowatt racks, liquid cooled cabinets, all of that tends to be the training jobs, where you're running workloads for a month on end just on a single training job. Once you have trained the neural network, that trained neural network moves into the inference validation systems, which tend to be more CPU heavy, but with a little bit of GPU to run through the inference validation. Completely different clusters, entirely different. One may be a DGX cluster, the other may be a flex pod or a white box CPU cluster with some GPUs. What does this look like from the data scientist? He's selected a framework, he's off, he's ready to go, he's got his Jupyter notebooks and IDE. He's picked a model that he's going to tune and a set of hyperparameters. He's read data from storage close to the pod. So this is where the pod comes in and data is being cached close to the GPU. And now he's building these TensorFlow threads that start to build up data flows into the GPUs and starts to then run the model through the epoch, sync the results from the model, and off you go again and again. What does that look from a storage perspective? Why does storage matter? What is storage doing in here? The number one goal is to keep the data scientist busy, which means you're going to be loading up those GPU systems to 100% utilization, which means you've got data flowing into the GPU constantly. That data is being read in the form of random reads of small images. Each image that is read may be a single record of itself, or you can aggregate a set of images into a single TF record aggregated file. Each file is read by a single reader job that is now mapped from a locality perspective to the set of GPUs or the cores, the tensor cores of these GPUs, and then you're now running through these training jobs. You complete one pass of the neural network, and then you read the data again with a lot of random switching, not only across GPUs, but across nodes themselves. So what's going on here? You've got a parallel file system, or at least some kind of scale-out file system. You've got a scale-out compute cluster with random reads across this cluster, doing mostly read jobs. So 80, if not 100% of the data is being read, with checkpoints that cause sequential writes, or synthetic data generation called GAN neural networks that again cause sequential writes. A combination of random reads, sequential writes. And where have we seen that before? We've probably rarely seen that before. Random reads in an OLTP database, that's something we see. Sequential reads in an analytics engine like Spark or an Oracle Exadata. But the combination of the two, not as often. So what did we cover so far? We covered the pipeline, the process of ingestion, the double click on the training cluster, and what are the bottlenecks, the system architecture bottlenecks that require a high performance compute along with high performance data, and the ability to bring random reads alongside with sequential reads and sequential writes. Very, very unique workload. So what about the software? Your question earlier is extremely valid because data scientists don't know hardware at all. They've got to run these jobs. They have no clue what this entails. And when you talk about all of the things that go into deploying the system, data scientists do not want to deal with that. So that's where the software stack comes in. We start out with bare metal provisioning. That's probably a multi-hour job. Once you provision the nodes, which is GPU compute management provisioning, we've got the compute nodes being automated with DPOps. So DPOps, which is the NVIDIA software, runs through, it deploys a Kubernetes cluster on the management node, deploys the basic services across the management nodes, provisions the compute nodes, deploys additional services, and is now set up to a point where you can start running these jobs. which is where we come in with the AI control plane.
So wait a minute. Can you go back to the previous slide?
Sure.
So this is deploying your solution, your NetApp solution.
So this is bringing up the cluster for the first time. So you've racked and stacked the ONTAP AI, compute, and network and storage. You have automated the deployment of software for the first time. This is a one-time setup.
And you guys are seeing that your customers have settled on Kubernetes and that's what they're running versus running their own custom in-house scripts?
Yes.
That's different than what I've seen.
So from an AI perspective, Kubernetes is certainly becoming the de facto choice. You'll certainly see some Slurm. There's certainly Slurm usage. If you're coming at it from an HPC background, Slurm is very much the de facto. And you'll see engines like Bright Computing with Slurm that is being used. It really comes back to, is this team coming from an HPC background, or are they coming at it from a AI out of grad school, doing their AI doctorates, and they're now looking at Kubernetes and Kubeflow. So it's two different.
Okay, but but an AI architecture is usually backed up. Everything you just talked about was machine learning. So really, it is an HPC type of architecture. So, and it's fine if that's what you're seeing most of your customers doing is Kubernetes, but it is really an HPC architecture.
Yeah, we actually think it is a variant of HPC. We actually don't think it is HPC because you see a lot of random small file reads. So the place where we can look at this as HPC is if you're doing a workload that is very large video-based AI, so video feeds, for example. But if you're doing computer vision and even NLP, these are random image reads where the size of the image is much smaller than your typical HPC workload. A typical HPC workload is sequential, parallel reads of massive files.
But what you were just describing was machine learning and deep learning, and those are definitely based on HPC architectures.
So we've seen customers go through that journey where they've started out with an HPC system and eventually reached the conclusion that HPC is not giving them the performance that they need, and they're starting out with ground-up architectures that are moving away from HPC. So this has happened over and over again, where they may start with a GPFS or a Lustre parallel file system, and then realize that you're getting opens and closes, and the overheads of opens and closes, the metadata overheads, the random read overheads, and the frequency of checkpoints alongside with the reads. All of that changes the workload to be different from HPC.
Yeah, the transition is from compute to data.
I agree.
Yeah, I can't name the number of places where we've seen that realization and say, okay, we've got to rebuild this thing. It's not just our old HPC infrastructure. So,
but we are seeing that GPFS is not good at handling small files. We are not seeing that this is not HPC. I mean, there are several HPC workloads that are based on small files. It's just that you have to choose the right file system in most of the cases. It's not just that it's not HPC. I mean,
in fact, what I've seen as well is in most of the cases, some of the organizations go with GPFS because it's been here for a long time, because it's the only thing they know, and because it gives them the assurance that it's going to work. But there's a lot of storage systems out of there which are good for HPC as well. Which are much more efficient.
Yeah, it absolutely comes down to where the team is coming from. If the team's coming from a background where they've been used to GPFS, they're going to start there. And in some cases, they're going to revisit it. In many cases, they look at what is the overall architecture. It's not just training in isolation, but it is how do you build that control plane as we go into the next view here across the pipeline. And when you talk about the control plane across the pipeline, you're now looking at the movement of data through the pipeline. So it's not just about the GPFS or Lustre parallel file system, but it is what are you going to deploy in the cloud?
Why do you need something in the cloud? Because you keep saying that too, and the data is not in the cloud. So like this seems like a very specific problem or application that you've built or that you're building. So like, why do you keep going to the cloud? Do you really think that anyone that does AI is going to have a cloud presence as well?
Yeah, that's a great question. So what we've seen is startups that are innovating in AI, data labeling. I'll take one simple example. Data labeling startups that are building semi-autonomous labeling software are building it as cloud native. So if you need to get data labeling,
but what cloud are they using? Because when did GPUs and things to actually do deep learning, and how long has that actually been available in the public clouds?
So GPUs have been around for about 6 or 7 years when you go back.
But not in AWS. They've not been
2-3 years.
Yeah. Okay.
But anyway, it's it's not a problem. So when you start a new machine learning project or deep learning, you choose your architecture. And for some companies, the least, the smaller of the problems is the infrastructure. I mean, there are so many layers on top, special business objectives, that you don't really care if you're spending money on the cloud for that. I mean,
the trick for startups is they're optimized to fail.
Yeah.
Right?
So they don't really care about it.
You stick it in the cloud because they're going to
the problem then comes if it becomes strategic and you have, several projects on it, and you say, oh, wow, it's becoming very expensive.
Well, if you're an investor in a startup who's doing some AI, like doing some data labeling, which is big business, you want to give them $5 million, but you don't want them spending $5 million on a NetApp AI cluster.
Oh, yes.
And then there's no money left for anything else, right? So they start in the cloud, and then they fail in the cloud, and there's nothing to clean up. There's no assets to disperse or to dispose of,
exactly.
Or to whatever, right? So the cloud is optimized for startups to fail in this area. The cloud AI processing is incredibly slow. The data rates that you get to and from the data lake is very slow. It takes 10, 50, 100 times longer for the AI to finish if you're running it in the cloud.
Oh, yeah, but people that are building very large, all the automotive companies, they are building their own AI farm. I mean, but they are used to build their own HPC farms as well. So they have teams working on it since forever.
It's more sense to do.
The
problem here is that these are data computers, not compute computers. The transition that you're seeing in AI is that you're no longer worried about the CPU. Your primary concern is the data and how you feed it into the GPUs.
Yes, so you need a throughput that is highly
The throughput.
And
the
so
throughput.
on that note, what I'm gonna sort of segue into is you're dealing with a variety of dimensions. You've got the data scientists who want to just get started. They don't want to wait on hardware. They don't want to pay for hardware, much less deal with the time that you need to deploy. So they go into the cloud because they can start right now. Their software, whether it be data labeling, whether it be inferencing, version management, whether it be the pipeline automation, these are software from startups that are being cloud native at first, at least. And so the cloud is absolutely seen when you're dealing with this life cycle for experimentation. As you get into production, the cost, the performance, the linear scalability, all of that brings it right back to on-prem. So when we go back to what is the NetAPI control plane, we talked about the one-time deployment automation with Ansible. And then we get into the ability to deploy with Kubernetes and Kubeflow. So we've integrated ONTAP with Kubeflow, where we are now able to deploy and manage the lifecycle of a Kubeflow job through the Trident storage plugins and the backend lifecycle management of storage. So what does that mean? If you're starting out deploying a Kubernetes cluster, the first thing we do is we deploy a Trident storage plugin, which is the backend, to manage storage on an ONTAP system or a NetApp system in general. The Trident plugin integrates into Kubernetes and claims the persistent volume interface so that when you start to provision storage, you're now provisioning storage from a NetApp system. So as you build out these Kubernetes clusters, data for the underlying system is being provisioned out of network storage. And that network storage, coupled with the compute stack, can be replicated across sites, whether it be in the cloud, whether it be other sites, whether it be at the edge. So as you build out these Kubernetes clusters, we've got the identical software stack, compute and storage, now federated using the data fabric, allowing you to start a cluster up and burst into the cloud, start in the cloud, and burst or reverse burst on premises, and go in both directions. So let's talk about some use cases. The data scientist started out in the cloud. Once he was done with experimenting and the hardware was provisioned, he can reverse burst on premises and spin up the job in production. The data scientist started in the cloud. He can reverse burst across sites. If you've got data science at corporate headquarters, production is across the different sites for the company. Now we are talking about reverse bursting into each site to run at those locations. Similarly, if you're retail, for example, you need capacity in the holiday season. You start out a job that's running on premises. You might get some additional capacity expanding out into the cloud. Kubeflow is becoming the standard or the de facto for managing the SDK for AI.
In the previous slides, are you saying that you start working on the cloud and then you move all your data set back on premises?
The small subset of data that was used for experimentation. So you don't want to look at this as, if you go too deep into deploying in the cloud,
okay, you're stuck there.
now you're stuck.
Okay.
But if you are in experimentation stage, you've got a data scientist doing small experiments, hopefully you're dealing with 10 to 20 terabytes of data.
Okay. I have to say that if you need to more 10 to 20 terabytes, there is no difference on the architecture you're using. But, it's nice to have if you have NetApp, but if I have anything else, it works anyway.
So where you start with the experiment is 10 to 20 terabytes. As you start to scale into production, now you're talking 100, 500 terabytes, a petabyte, and that thing takes a life of its own as you start to expand.
No,
So
but we're starting talking about moving 10 terabytes.
Yeah.
So 10 terabytes is 10 terabytes. So I start working in the cloud, and then I choose an architecture for my own premises. They could be totally different. I mean, I do not want to plan in advance the architecture that I will use on my premises anyway. So I start to experiment. I decide that AI becomes strategic. Then I choose a partner for my, and maybe NetApp is cool for a reason, and I go with NetApp. But actually, potentially, I started working on Microsoft Azure or whatever, and I didn't choose NetApp to start with because there is VXFS from
and hopefully you started on Azure NetApp files because that gives you some level of commonality. So there are some options with CVS and Azure NetApp files.
If I'm not a NetApp customer, I mean, you need to have a very, very long-term strategy for these kind of things to think about. I start with NetApp because I will buy NetApp on premises. Because if you're talking about buying millions of euros of infrastructure, there is everybody.
So we are building data movers.
Table.
So we're building data movers to go from object into NFS. So we're moving data from S3 to NFS. We're building data movers from GPFS and Lustre to NFS.
Are they ready?
Yes. We've got POCs ongoing with customers to move from MapRFS to NFS. So the data mover is the key ingredient because you're right. There's all kinds of data sources. And it's not enough to just say everything's got to be an NFS. It's not going to be an NFS. So we are building data movers across every data source and adding as we go. So today we've got HDFS, MapRFS, GPFS, and S3. And we're going to keep expanding that list. And we're building POCs. We are sizing the data movers. We're optimizing the data movers to do parallel data movement. So these are things we have today. Absolutely building that. So this is where you end up. Kubeflow as the SDK, provisioning a Jupyter notebook for customers. So you end up with a Jupyter notebook per data scientist, provisioned under the Kubeflow SDK, and Kubeflow under the covers using Kubernetes integrated with Trident, provisioning storage out of the NetApp data fabric, whether it be in the cloud, whether it be on premises. Being able to take you from one location to the other to burst, reverse burst, or expand. And so here's what this stack eventually ends up like. You've got a data scientist workspace, which is a Jupyter notebook, integrated and offered through the Kubeflow SDK, connecting into data through our Trident persistent storage plugins, built and deployed using Kubernetes clusters across a variety of GPU nodes, on-prem or in the cloud. Where are we going from here? We're building vertical architectures. There's 4 areas we're focused on. We're building autonomous training architectures, medical imaging architectures, genomics, and use cases like fraud. What do they look like? We're starting to build out these pipelines specific to products that focus by use case. So NVIDIA Drive, For example, starting to look at integrating ONTAP AI with NVIDIA Drive. And what does that mean in terms of the data flow? How do you size it for the training jobs? And then how do you build separate architectures for training and replay or simulation? Similarly, we're starting to look at medical imaging and building out these NVIDIA Clara architectures on ONTAP AI. How do you take a Clara system and build a pod that is a Clara deployment that can give you the assisted annotation as well as the labeling? So what is the benefit of this? Why is every hospital and every higher ed institution focused on the medical imaging practices looking at AI? What's going on? The bottom line is you can take images of any type and start to look at AI as transforming that workflow. Medical imaging is a classic example. If you're paying a radiologist to be able to look at these images and you're bottlenecked on the number of radiologists, the location, and the physical wear and tear of looking at these images, AI automation gets it down from where you could look at 50 to 70 hours worth of charts to now looking at 500 hours worth of charts using AI-assisted medical imaging. We're seeing this across the board. Odds are the providers that are handling healthcare for many of you in the room are using NetApp today because we're deployed with healthcare providers focused on medical imaging, focused on medical fraud prevention, focused around automation of the nurse or the physician assistant use cases. So we're starting to build these pods with Clara and with Drive. And what does the pod look like? Images coming out of the departments into a hospital backend, into a data lake, going through training with the neural networks pushed back out, so you have AI-assisted medical offices for that medical imaging use case. Sizing the systems out for performance so that we can then deploy what is needed for that use case. Same thing with genomics. Genomics jobs on CPU clusters taking forever, now getting reduced down with GPU cluster deployments using vendors like Parabricks on ONTAP AI. Similar disruption around the structured data set. Everything we talked about was unstructured. Now starting to look at structured data with GPU databases and the acceleration of structured machine learning with GPU databases. So the bottom line, why NetApp AI? We are offering a full stack solution across the high performance, across the capacity, across both the HPC and the AI teams where they need Slurm with InfiniBand and GPFS. We have that covered with E-Series. We've got them covered for the Ethernet cloud-enabled use cases. Building out control planes with Kubernetes, Kubeflow, automating with Ansible. Building out the data movers that are needed across the variety of data sources, HDFS, S3, MapRFS, and so on, and the federations from core to cloud. So where are we at with customers? We start to build out the use case. We do workshops with customers. Most fascinating is we've been doing POCs, multi-week POCs with accounts.